remember my first impression of disappointment. Is that all? And I remembered that I had all these absorbing material, so when it faded, I tipped the welding glass and looked down at the sand. Now, you know, it was before dawn and quite dark. But when I tipped the welding glass, looked down at the sand, it was as though you removed the curtain in a dark room and the bright sun came in, and then I was impressed.
Nuclear reactors could... I'm sorry, Mr. President. Nuclear reactors could provide power almost indefinitely. Greenhouses could maintain plant life. Animals could be bred and slaughtered.
Mr. President, we must not allow a mine shaft gap.
Sir, I have a plan.
Einstein's famous equation, E equals mc squared, told us that energy and mass were interchangeable. It gave us the knowledge to build weapons of mass destruction and the knowledge to understand how our universe was born. When a nuclear bomb explodes, a tiny amount of matter is completely annihilated and converted into energy. But in the Big Bang, the exact opposite happened. Pure energy was converted into matter.
I know, tell them I won't be long. We'll meet again. Don't know where, don't know when, but I know we'll meet again.
How is it possible to construct heavy objects out of objects that don't weigh anything? And the answer to that challenge comes from Einstein's second law, m equals E divided by c squared. If you think about E equals mc squared, famously, what it suggests is the possibility of getting large amounts of energy from small amounts of mass. And so it suggests things like the possibility of making nuclear weapons. But if you write it this way, it suggests the possibility of explaining mass purely in terms of energy. In fact, really, this should be called Einstein's first law, or maybe his 0th law, because this is the form that he actually had in his original paper. Does the inertia of a body depend on its energy content? So right from the beginning, Einstein was thinking of the possibility of creating mass out of pure energy. And remarkably enough, that's what actually happens in our modern theory of quarks and gluons and the strong interactions.
Now, what are the quarks? Are they actually real objects? Well, my experimental friends are making a search for them in all sorts of places. One atomic spectroscopist friend of mine calls me up sometimes at midnight to report his progress in a search for quarks in seawater. Most things with curious chemical behavior in the ocean end up eaten by oysters. And so now he's grinding up oysters and looking for the atomic levels in the oysters. So far, though, no quarks.
His 3 quarks could combine in different ways to reproduce the properties of this enormous particle zoo. It would simplify, organize, predict. It was a great scientific advance.
Because there are 6 quarks altogether, divided in 2 different triangles of matter, the strange quark triangle that makes neutron stars and the top quark triangle that makes black holes, their combinations in triads give birth to 20 possible particles, which means 20 St. Nobel Prizes for those scientists responsible for their discovery. And so, a new race started at CERN to capture those 20 St. Nobels.
We were literally drowning in subatomic particles. One year, out of sheer frustration, J. Robert Oppenheimer, father of the atomic bomb, stated that the physicist who does not discover a new particle that year should win the Nobel Prize in physics.
So they set out to find them. They would look and look and look for 30 years, and they would find nothing.
Since cosmic rays are bigger particles, lonely atoms that never lump in enough numbers to form a mass bomb, mass bombs, only happens inside stars, where the density of matter implodes those atoms, liberating its strong quarks in nova reactions, and now it will happen also on planet Earth.
While we see the outward explosion as a supernova, this masks the inward implosion. The core is collapsing into the most dangerous object in the universe. The density becomes so great in the center that gravity sucks in time and space itself from the outside universe. A black hole is born.
The difference between an explosive atomic bomb and its inverse, an implosive mass bomb, is obvious. Because its combustible is the external mass of the cosmos, a mass bomb only needs a small quantity of detonator to explode, which can be produced in a super collider on Earth. Thus, mass bombs can have any size as long as they find mass to keep growing. The smallest ones, called novas, explode planets and stars, leaving behind a trail of destruction. Some, called quasars, blow up entire galaxies. Astronomers even speculate that the origin of the universe was the Big Bang of a mass bomb.
Today, astronomers see the universe expanding. Imagine running the expansion backwards. Billions of years ago, everything must have been packed together at enormous density. It seems incredible, but we think that the matter making up everything we see in the universe today, everything, the buildings, trees, people, planets, stars out to the most distant galaxies, was once crammed together into a volume smaller than this. And then
now CERN will try to replicate the Big Bang to explore the limits of entropy, creating mass bombs without any safety measure here on Earth.